Geometry, section 11.7, similar solids. I got a definition here of similar solids, and it simply says that they have the same shape and all corresponding dimensions are proportional. Let me give you a quick example. We'll use things like cones and, hexagonal pyramids and prisms and that kind of thing. But just to give you an extreme example, let's suppose you have a car in the parking lot and then you have a toy model of that exact car, okay? What we would know is if they are similar solids, which they should be if one is an exact model, then all of the dimensions are proportional, as this definition says. So for example, if the similarity ratio, we're about to use that word, is 50 to 1, big car to little car, big car to the model, the bumper on the big car would be 50 times longer than the bumper on the toy car. The radius of the front left wheel would be 50 times that of the, whatever linear dimension you want to compare. If it's truly proportional, if it's truly similar solids, that's what would happen. Whatever they are. If you find we're able to measure it around, at the same location, I'm going to get off this example now, but we're talking, that's a perimeter, so that would be a length. Okay, now similarity ratio. This is a word we used in section 10.4, and we're now going to just kind of expand this for three-dimensional figures. It's the same phrase, the ratio of corresponding linear dimensions of similar solids. Okay, so again, if we can compare it on that car, that ratio was 50 to 1, and it holds true for all the linear dimensions. Linear meaning line, meaning one-dimensional, meaning what I called in section 10.4 level 1. Those are lengths. Level 2 was areas. For section 11.7, that's going to work in as surface area and areas of faces and that kind of thing. And then we're going to add in a third level, which is going to be volumes. Okay, so let's look at an example. This here says, are the two solids similar? If so, give the similarity ratio. Okay, now to compare that, so here's the radius of the base, here's the radius of the base of the large one. We could compare those in a fraction, it would be 3/9. That's 1/3. If I compare 8 over 26, that's not going to be 3/9. That reduces to 4/13, and that's as low as it goes. So those are not the same fractions, so the answer would be no, they are not similar. Here's a question I like to ask. Change one number and make it so that they would be similar. You could simply change, so again, 1/3. If we wanted 1/3, we could change 26 to, what would be 24? If that height were 24, then you would have similar solids. 3/9 is 1/3, 8/24 is also 1/3. Okay, that's not what they asked us to do, but just kind of a side question there. All right, now back to the notes because I didn't talk about the theorem yet. So with all that in mind, if the similarity ratio of two similar solids is A over B, then the ratio of their corresponding areas is A squared over B squared. This looks very similar to something we saw in section 10.4. Back then we were dealing with two-dimensional figures exclusively. And right here, in essence, we are still dealing with a two-dimensional figure because we're talking about surface area. It's a three-dimensional figure, but we're talking about surface area. That's why the units in all the surface area sections of chapter 11 used feet squared, meters squared, miles squared, whatever, not cubed. Okay, now the new part is this. And the ratio of their corresponding volumes is A cubed over B cubed. Now, you probably could have guessed that, okay? And that's going to be the case, and we're going to see that in the examples. So here's an example. Find the similarity ratio of two similar cylinders with surface areas of 98 pi feet squared and 2 pi feet squared. So you got this really huge cylinder that's got one surface area and then a much, much smaller one, which is the surface area that is 2 pi. I guess the first thing to point out here is the fact that they are cylinders doesn't even matter. We're going to compare these in a fraction. Okay, now 98 pi over 2 pi. So a lot of times they will designate which one should go on top, kind of a first, second kind of thing. I don't think they did that here, so I'm just going to make the fraction the way that they have presented the information. So 98 pi came first. I'm putting that in the top of my fraction. And this fraction reduces. Now, an emphasis that I started making in section 10.4 that I want to make here again is that when I reduce this fraction, you have not changed its value. You have not gone from level 2 to level 1. You have not found a similarity ratio yet. The pi's here would cancel. 98 over 2 is actually 49 over 1. This is not a similarity ratio. This is still a ratio that describes their surface areas. For that matter, it's a ratio that describes their lateral areas. It's a ratio that describes the area of the circular bases, all of that. Okay, that's the two-dimensional nature of this. What we need to do to take it to level 1, from level 2 to level 1, is to square root it, which means to square root the top and the bottom. So that would be 7 over 1. Now, I like the fraction. I mentioned that in section 10.4. If you said 7:1, that's correct as well. But do make sure that it is reduced. Either way. I like the fraction better, though. Okay, a couple more examples. 2 similar square pyramids have volumes of 48 cubic centimeters and 162 cubic centimeters. The surface area of the larger pyramid is 135 square centimeters, 135 square. Find the surface area of the smaller pyramid. So notice they're giving us information on level 3, and they're asking for information that's on level 2. Okay. Now here's the way you're going to want to do this. I don't ever teach, and I don't even really know how it would go to teach this, that you can go from level 3 to level 2 directly, or from level 2 to level 3 directly. What we should do is take everything back to level 1, and then if we have to go further than that, we can do that. Okay. So when they tell me that the volume is 48 centimeters cubed and 162 centimeters cubed, I can put that into a fraction. This is a fraction that describes, a fraction that describes volume. Once again, 48 and 162 are not convenient fractions are convenient numbers to have to take the cube root of. So what you're going to want to do is reduce that fraction. It reduces to 8 over 27. Okay. And that's fun because 8 and 27 are both perfect cubes. If I take the cube root of that, that's going to be 2/3. Okay, now again, major emphasis on this. 2/3 is the similarity ratio. 2/3 is the similarity ratio, not 8/27s. 8/27s describes their volumes. That's a different number. That's a different comparison of numbers. 2/3 describes lengths. This is a similarity ratio. If they asked for it, or if they asked for the ratio that describes, whatever, a comparison of two lengths, this would be the answer. But they didn't ask for that. They did say find the surface area of the other pyramid, of the smaller pyramid, given that the larger one's 135. So now what we need to do is we need to take this to level 2. Take 2/3 and square it. That's 4/9. Okay. So on this particular problem, we've been at every level. We went from level 3 down to level 1, up to level 2. 4/9 describes areas. And we did all that so we can now answer the question using the fraction 4/9. We can set it equal to a fraction that incorporates the 135. Now read carefully. The surface area of the larger pyramid is 135. That means it needs to go with the 9. The 9 is the larger number. You certainly could do 9/4. If you did this fraction backwards, reversed top and bottom, then all this would just be reversed and you could do 9/4. You would just have 135 over x. But I'm going to do this one, x over 135. As soon as you cross multiply either one of these problems, you'll have the identical thing. Again, we've done a lot of cross multiplying this year, so let me just roll to the answer. It is 60. You solve this, x equals 60. 60 square centimeters. Okay? One more. A box of detergent shaped like a rectangular prism is 6 inches high and holds 3.25 pounds of detergent. How much detergent would a similar box that is 8 inches tall hold? Round your answer to the nearest tenth. Now, real quick drawing. I have seen boxes like this in my own home. You probably have too. I'm thinking of like the dishwasher soap, right? Now, I think you're going to be a little bit shocked at the answer that we get, right? We only increased the height of it from 6 to 8. That doesn't seem that significant. But let's take a look at how different the answer actually is. Okay. Now look, they said 6 inches to 8 inches. Those are two numbers that I can compare, and I will reduce that fraction to 3/4. This is a similarity ratio. A height is a length, and length is working on level 1. Okay. Now we want to go to level 3. Quick side note on that. We are talking something in weight. It's 3.25 pounds. Everybody should agree with this. I don't want to get into this too long, but that incorporates volume. It's obviously nothing to do with surface area. The weight is going to fill the space. You fill an empty box with dish detergent, powdered dish detergent. It's going to fill the space, and weight and volume. There's a conversion for weight and volume. Okay, so when they say this, when they present this problem in pounds, we're obviously on level 3 is what I'm trying to say. So take 3/4 and cube it to the third power. That would be 27 over 64. 27 over 64 describes volumes. And yet again, we're going to solve a proportion. Now, one more time, where does the 3.25 go? With the 27 on the top or with the 64 on the bottom? It's the smaller one, right? It's the one that had the 6-inch height. The bigger one is 8 inches high. So 3.25 over x. Okay. Now, before we finish the problem, just take a guess as to what the volume of the bigger one's going to be. We expanded from 6 to 8. What do you think the volume's going to be? Just take a guess. Wait, I really mean to say weight. How much do you think it's going to weigh? It's going to weigh about 7.7 pounds. The solution here is about 7.7 if you solve using the cross-multiplying method. I think that's a little bit shocking, but it is true, right? Now, the reason that is true is because the height expanded from 6 to 8. The depth would also expand. The width would also expand. And that is the nature of the three-dimensional volume. So even though the lengths only got a little bit longer, but basically went up from 6 to 8 by 33%, the volume actually more than doubled. I just thought that was interesting. Thanks for tuning in.